Alright class, we're going to start solving exponential and logarithmic equations today. We're going to be using set notation the whole time. So this first one we've done a billion times now, guys. This is equating exponents. If two powers with the same base are equal, then their exponents must be equal. We've been doing this now since chapter unit 4. So we did a little bit with it on the first quiz as well. So these two should be review. You want to get the bases the same if possible. So you should know that this is 2 squared to the 3x, and this is 2 cubed to the x plus 1. So the bases are now the same. The powers are 6x and 3x plus 3. Do not forget to distribute that. 3x equals 3, x equals 1. There's no restriction on the domain, so that should work fine. Okay, over here, 32 is 2 to the 5th power. Alright, and then we just set that equal to 2 to the 4x. So we can set the exponents equal to each other. So we get 5x minus 5. Negative x equals negative 5. So we get x equals 5. And that should work as well. Okay, so that is a review. No problem with those. So here is where we can now do these other ones algebraically. When it's not possible to write each side of the natural log equation with the same base, we can solve by taking the log of or natural log of both sides. Because we learned it's like the power property. If these things are equal, then we can say that the natural log of 2x to the x is equal to the natural log of 7. Okay? Those are equivalent. It's just like setting the bases equal and equaling the exponents. We can log both sides here. Why we do that though, this is the best part. We can now use our property we learned yesterday and say, okay, now I have this. What's true about exponents? I could put those down in the front. So I get x times the natural log of 2 is equal to the natural log of 7. Remember, the natural log of 2 and the natural log of 7 are just numbers. Okay? Then I can solve for x by dividing by the natural log of 2. So I get x is equal to the natural log of 7 over the natural log of 2. This is not the subtraction property because it's two separate logs. Okay? It's not the log of 7 over 2. It's just the natural log of 7 over the natural log of 2. So this would be the exact answer. So if I said I want the exact answer, you would leave it like this. Or if you type it in your calculator, you can type in natural log of 7 over natural log of 2. You get that as your decimal. And that would be correct. All of these should work. Okay, now usually with any random base you can use natural log or log, but if you have a base 10 or a base e, you want to either use the natural log or the log because it makes it simpler. For example, if this is e to the 3x equals 12, I know that natural log of that will cancel that out. So I'm going to say the natural log of e to the 3x equals the natural log of 12. I just natural log both sides. Now I'm going to put this 3x down in front. So I get 3x times the natural log of e is equal to the natural log of 12. Okay? Again, think of these as numbers. You can type them in and get a decimal. You guys should know that this number is equal to 1. So I get 3x is equal to the natural log of 12. And then x is equal to the natural log of 12 divided by 3. No, you cannot divide the 12 and the 3. They're different entities. You just type it in as is. When in doubt, don't simplify, just type it in. Because a lot of you guys might try to simplify it and make it the wrong thing. Okay, so this one here, you do not want to log it, so don't log both sides until the exponent is isolated. I'm sorry, the exponential piece, I should say. Okay. What that means is I don't want to log both sides until that 4 is moved. So I'm going to move the 4 over, and I get 10 to the 2x minus 3 is equal to 21 minus 4, which is 17. I'm going to rewrite this with logs on both sides, and I'm going to use log instead of natural log here because it's base 10. So log of 10 to the 2x minus 3 equals log of 17. I'm going to bring this down now because I can use that property. So I get 2x minus 3 times the log of 10 equals log of 17. This turns into just 1, so I don't need that anymore. So I get 2x minus 3 equals log of 17. 2x is equal to log of 17 plus 3, and x is equal to log of 17 plus 3 all over 2. So you can type that in your calculator. Be careful how you type it in. Make sure it is correct. And you should get that this is approximately 2.115, and that will work. All these exponential ones should work, although you should check to make sure you did the math right. Again, we need to isolate, so I have 5 to the x plus 2 is equal to 22. Here it doesn't matter which log base you use because we have a 5 here. Again, you only want to use natural log or log because of the buttons in the calculator. So I'm going to use ln. So then this comes down in front. So I have x plus 2 times the natural log of 5 equals the natural log of 22. I'm going to divide by the natural log of 5 because that's attached by multiplication. So I have natural log of 22 over natural log of 5 equals x plus 2. Then I'm going to subtract. So I type that into my calculator, and I get that it's approximately negative 0.079, and that will go in brackets. Okay, so that's how you solve using logs. That's why logs are helpful, are those properties we learned yesterday. Now we can solve all those ones we were using our graphing calculator with earlier in the year. So, solving logs with same base. This is kind of like the exponent. If you have log base a of something equals log base a of something else, then x and y have to equal. You cannot take a log of a negative number, because a positive number raised to any exponent will never be negative. That's why the domain is always greater than 0. Since by definition, the base is always positive, you can never take a positive number to a power and get a negative number. Okay? Like this. We get 4 to the third. That gives you 64. 4 to the negative third gives you 1 over 64. We'll never get a negative number. Okay? So, let's keep going then. Solving with the same base. These are both the same bases. So because of that, and again, it's only one equal to another. If you have like a plus in here, you're going to have to use log properties to put it back together, and we're going to do those tomorrow. I can just say that if the logs are the same, then these exponents are the same. It's like the reverse of what I was just doing. So I solve and I get 4x equals 8, x equals 2. Double check, put 2 in, here and here. So I get 10 minus 1 is 9, 2 plus 7 is 9, 9 is greater than 0. So I can say that the answer of 2 is a solution. Okay? Again, we can set both of these equal because the bases are equal. So x is equal to 8x plus 14. Negative 7x equals 14. X equals negative 2. Now, here some of you guys might be like, oh, it can't be that. Okay? So let's check. Let's check. I am going to plug this in here, and I get a negative 2 times 8 is negative 16 plus 14 is a negative 2. And I get a negative 2. Again, you cannot have this, so this is not a solution here. Okay, this is not a solution. So, that means there actually is no solution to this problem, and negative 2 doesn't work. You have to check, because the thing here can never be negative, and both of those turn into a negative 2 there. We're not going to, there's no exponent that'll get us a negative 2. Okay, so that's our final answer for this one. Now, the last thing we're going to do is rewriting back to exponent, or reverting back to exponent form. So if you have a log equal to a number, just rewrite it in exponential form to help you out. And then sometimes you'll have to use logs. But let's see what we have. So remember from the first day of logs, to rewrite it, this is the base, that's the exponent, and then it's going to be equal to that. So 5 squared is equal to 3x plus 1. I just rewrote it. 25 is equal to 3x plus 1. 24 is equal to 3x, so x is equal to 8. Do a quick check. If I put an 8 in there, sure enough, it's positive, it'll work. So we have 8. Here we have 3 to the third. is equal to x plus 5. So I have 27 is equal to x plus 5. So x is equal to 22. Again, a quick check will work. Okay. So now I want you guys to try these. There's basically 3 types of problems here that we did today. One is a review. The last 2 are not. Okay. Again, you know you need to use logs if you can't get the same base number. But since this first one you can, you should, by the way, pause the video and try these. I'm going to do them right now. But if you want to try them before you see the explanation, just pause your video. This is 9 squared to the 3x minus 2. Now, you could also go down to base 3s for both of these, but as long as you get the bases matching, you're fine. So I get negative 4x equals negative 4. So I get x equals 1, and that'll work. Alright, so this problem here, I know I have to use logs because I can't get base 10 of these. So first thing I do is move this over, and I have 10 to the 5x plus 4 is equal to 35 minus 8, which is 27. So now I'm going to log both sides. And the reason why I'm using log base 10 is because I have a base 10. So it'll help me out later. So this is going to come down in front. So I get 5x plus 4, this whole thing, times log of 10, which is just 1. So that's going to go away and turn into a 1, right? So then I can just start subtracting the 4 over. So I have 5x is equal to log of 27 minus 4. X is equal to the log of 27 minus 4 over 5, which is approximately negative 0.514. And again, that should work because we didn't start with a log, which gives you a domain restriction. This one we're going to have to check at the end. This one's a rewrite, so we take 5 to the second power. Always try rewriting into exponential to see if that will help you. So you get 25 equals x minus 4, x equals 29. And sure enough, 29 minus 4 works in there. So we are all set. Okay, so that is the different ways you can solve. We're going to do more difficult ones tomorrow.